Welcome to AP Podcast 10.1. This is on intermolecular forces. Now, what we've been dealing with so far is the intramolecular forces. And when I talk about those, I'm talking about those ionic bonds and those covalent bonds. Those are in between the atoms. In other words, if I take a little water molecule right here, and this is covalently bonded, an intramolecular force is this thing. This thing is holding the atoms together. All right? An intramolecular force would be something like this. Again, I'm going to draw water. Imagine water in the liquid state. Well, it turns out that water is attracted to each other by a force there. And this is an intermolecular force. So those forces are really important. They're the thing that hold all the molecules together in condensed states. So, for example, instead of everything being in a gas, we have things in the liquid or the solid state. And that's due to these intermolecular forces. Very, very important forces. So here's a simple summary on it. Here's our strong forces, or strong bonding forces. And this is the intramolecular forces. That's covalent bonds and ionic bonds. And then we have these weaker forces. These are the inter. Okay? That's dipole forces, which you know about. Hydrogen bonding we're going to talk about, and London dispersion forces. But those are really important things. Otherwise, like I said, things would be in a gas state. So imagine water in the liquid state. Okay? And we go ahead and heat it up. And we turn it to a gas, right? Now, when that occurs, all you're doing is taking those water molecules and separating them from other water molecules. You're not taking a water molecule and separating it into its atoms, which is a good thing, because that would be a chemical reaction. Okay? So a phase change is what occurs when you break these intermolecular forces. And in order to do that, of course, look at that. What did I have to add? I had to add energy. So energy overcomes these intermolecular forces. And that's how we can change things from a solid state to the gaseous state to the liquid state. All right? So let's look at each one of these. Here's the first one, dipole-dipole forces. Now you already know about these. You remember where our polar definition comes from. Remember our HF molecule? Okay, the fluorine was a little more electronegative and the hydrogen was a little more electropositive. And what was happening there is that those molecules were kind of lining up. So we would get another molecule that would line up with its more electropositive side. And this allows those molecules to kind of stick together, so to speak. It's not a very strong force. In fact, look at this. It's only 1% as strong as covalent or ionic bonds. And as you get further away from each other, like the gaseous state, it becomes a very, very small role. So just a little picture here. Look at this. So this is kind of a visual what's going on. I've got this molecule with a more electropositive end. Oops. Alright, a little glitch here. I'm going to try this again. So imagine I have this molecule right here, more positive end, more negative end, and they line themselves up. Okay? And then if you can imagine a whole bunch right here, then you have something that's attracted to each other, and it is in the liquid. Okay, my computer's crashing with that picture, so I'm just going to move on to hydrogen bonding. We'll look at the dipole in just in class if it doesn't make any sense. Now here's kind of a special dipole force, and the important thing about this one that you really got to focus is it's only for elements bonded with fluorine, hydrogen bonding with fluorine, oxygen, or nitrogen. Alright, so there you go. Oops. And so just to remember it, I like to tell students phone, whether it's phone, home, or whatever. But you've got to remember those three because it's really important. Hydrogen bonding is a really special type of stronger dipole. So what you have happen there is, since you have let's imagine an oxygen atom. Remember, it's only got electrons in the second energy level, right? Well, then that's the case for all three of these. And so you've got electrons that are very close to the nucleus, and then you have a hydrogen attached. And so what that really does is allow a very strong electronegative force to be on the oxygen, nitrogen, or hydrogen or fluorine side, and a much more positive side on the hydrogen side. And so it's really important. And what this does is this affects the boiling point. And I've got a diagram to show, and hopefully my computer won't crash when you see it. But look at this. Here's hydrogen. Here's the boiling point of hydrogen, or pardon me, oxygen, hydrogen, water. Here's HF, the boiling point. Here's ammonia. So look how high those boiling points are. And if you look in their family, sulfur, selenium, look how much higher it is for oxygen compared to those other in its family. Same thing with all the halogens. Look how much higher HF is than that. Same thing with ammonia. Okay, and then you can see the carbon. It's kind of odd, but it doesn't have the strength or the forces it takes to overcome to get that boiling point at such a high, pardon me, I should say that again. The forces aren't so strong that it's tough to boil it at a higher temperature. So that's why hydrogen pardon me. Jeez Louise. All right, let me try this one more time. That's why oxygen, fluorine, and nitrogen have such high boiling points. It's due to this hydrogen bonding. So it's a very important dipole-dipole interaction that you want to make sure you're aware of. And here's a really good diagram of water. So you can see how the oxygen of one water will line up with the hydrogen of another, and so on and so on. So what that does is it gives it a pretty strong intermolecular force, and that's why it takes such a high temperature to boil water. All right, so let's move on to the last kind, London dispersion forces. Now, there are many molecules out there that have no polarity. Let's just imagine we've got a bromine molecule floating around. Okay, now, bromine is in the liquid state at room temperature. How can that be? There's no reason for those molecules to coalesce and condense. But it turns out that we know what happens in real life. We know there are many liquids that are nonpolar. And so the only way that can happen is that we must have some kind of slight polarity. And this is the weakest of the forces. All molecules exhibit London dispersion forces. And basically what you have, imagine an electron cloud around this molecule. Well, remember, electrons aren't static. They're moving around. So at any one point in time, maybe the electrons are more centered over this bromine, giving us a slight electronegativity. And over here, that would cause us to be a slightly positive. Well, what would that do to another bromine that was right next to it? Well, this positiveness would cause electronegative side to occur, and so it kind of goes from one molecule to the next, and it momentarily gives us some dipole. It's kind of an instantaneous thing. And so what you do is you get a little bit of attractive forces because of this instantaneous dipole. And it's a really important thing because it's a fact in nature. Otherwise, we wouldn't have liquids in nonpolar molecules. But what are the important things about London dispersion forces? Well, they're very weak. They're short-lived. Okay, they last longer at low temperature. Does that make sense to us? They last longer at lower temperature. Well, what happens to molecules at lower temperature? They slow down, right? So that should make sense to us that they slow down. Therefore, those London dispersion forces will last long enough. Okay, and then here's something that's really important. LD forces. Think about this. If I have a molecule that has more electrons, it could be more polarizable. Now, this word right here, I can't tell you how important it is. It pops up all the time in the texts. It pops up on any kind of information you read about London dispersion forces. And it's something that I'm looking for and the College Board is looking for when you describe what's going on with London dispersion forces. So when we talk about a bigger molecule, if we have something like a CH4 that's nonpolar or a C2 H6, okay, this thing right here has more electrons, right? More electrons means it's going to be more polarizable. So if I was looking at the boiling point of either of those two, I would expect this one to be greater because it has more electrons. It could be more polarizable, and therefore the London dispersion forces would be stronger in that one. So it's really important that you realize that. Now you might see if you read a textbook or you look online, you might see van der Waals forces listed, it's the same thing. So what I want to do right now is just look at a couple problems from your text and see if we can't figure out what's going on. All right, so here it goes. Identify the most important types of interparticle, intermolecular forces present. Well, what kind of compound is this right here? Okay, that's an ionic compound, right? So we've got ionic forces. What about something like this? This is a nonpolar molecule. Nonpolar. So what kind of forces do we have? We have London dispersion forces. What about something like this? Same kind of thing. Non-polarizable. Now, if some of you are wondering, well, isn't there hydrogen bonding? Look at this. Yeah, there is fluorine, but what are we missing? There is no hydrogen, right? So there's no hydrogen bonding going on there. CH3, well, if I were to draw that out, I would draw it like this. Okay. Now, this thing, hopefully you'll recognize, is polar. The electron cloud, or the polarity of this molecule, is going to be much greater on this side than it is going to be on this side. So this is polar, or if we're talking about the forces, we're talking about dipole. Okay, and you also have LD forces. Something like this, ammonia. Again, if you're not sure, just draw it out. That's going to be both polar, and you'll have LD forces. NO, there's going to be a little polar, mostly LD, and then BF3, you're going to have only LD. All right, last one. Pause the video for a second, look at these, and figure out if you can rationalize why there is a different boiling point for each one of these. Okay, let's see how you did. Now, they kind of start you off with a tough one. If you look at these two molecules, you've got the same number of carbons and same number of hydrogens. But for some reason, this one boils at a higher boiling point. Well, in this case, it turns out because this is a long chain, it's more easy to polarize this thing than this big tetrahedron right here. So that's why that one has a greater boiling point. Now let's look at these two. Wow, one at 79 and one at negative 25. Okay, what do we have here? Well, this thing is polar, so there is a dipole going on. This, however, look at this. Since it has an H bonded to an O, this thing has hydrogen bonding. Okay, so that has hydrogen bonding, therefore it's higher. It has a higher boiling point. These two right here, HCl, HF, again, since H is bonded to a fluorine, this thing can exhibit hydrogen bonding, whereas HCl cannot. Down here, wow, look at these two differences. Did you realize what this is? That's an ionic compound. The only way you can melt that is to break the intramolecular forces, and those are very, very strong. Okay, so that's why that one is. These two right here, well, hopefully you went, hey, this one has more atoms, therefore more electrons, therefore it's more polarizable. And so that's why that one's greater. Then these two, okay, now some of you might look at this and go, oh, well, there should be some hydrogen bonding. But if I were to draw that out, it would look like something like this. I'll put my two electrons there, C, and then an H, 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 C, and then an H, and an H, and an H. So this thing is polar, but what does this thing have right here? Oh, pardon me. This thing's polar. This thing is nonpolar, right? So all this has is LD forces, and then dimethyl ether is polar. So that's why, even though it's a low boiling point, it's higher than that one. Okay. Hopefully that worked out. We're going to spend a little bit of time in class working on these, because these are not too bad once you get the hang of it, but at first they're confusing. So hopefully everything went okay. We'll see you in class.